Okay guys, today's video is on doing performing one type of calculation, and then the other is going to be talking about how precision and accuracy differ. So both of these that we're going to cover are ways that you can describe or analyze data. So for the first one, we're going to talk about, we're going to go up here to where what looks like a bullseye or a dartboard. It says, look at each target and decide whether the hits are accurate, precise, both accurate and precise, or neither. So accuracy has to do with how close you are to the actual value. So last week we were solving for density, right? And it was said that the density of aluminum was 2.7 grams per cubic centimeter. And let's say that you took the mass and volume of a piece of aluminum and you found this is the actual or correct value for the density of aluminum. I'm going to put D for density, but let's say you solved for it and you got 2.71, okay? So if that's what you got, then that's really, really super close to the actual or accepted value. So to be accurate means that you actually have data or results that are really, really close to what they should be. Now, precision, on the other hand, so that's what it means to be accurate. So accuracy is results or a result close to the actual, or sometimes this is called the true value for that measurement, okay? So accuracy are results or a result or results close to the actual or true value. All right, so in the case of this bullseye, what we would say would be the actual or true value would be actually hitting right on the bullseye, okay? That within this bullseye would be accuracy, okay? That would mean that you're hitting it exactly where you're supposed to. Now, precision is different, okay? Precision is another way to describe data, but precision is how close a set of measurements are to each other, all right? So it's basically having things within a close range of each other, having them really tightly, like, that is, let's say that you measured, let's say that you took that aluminum and you measured it 3 times and you got 2.72 grams per cubic centimeter the second time, and you got 2.71 again on the third time. Right here, your 3 sets of measurements are really close to each other, which would mean that you are very precise, okay? So you've got precision. So precision has to do with basically with grouping, okay? So how well, in terms of darts, like if you're playing darts, or like with this bullseye, and this in terms of your hits, if your hits are all really close to each other, kind of like all of these density results are all really close to each other, that's known as precision, okay? So precision is the range and how close, how small that range is in terms of measurements being close to one another. So so we're going to look at these dartboards. If accuracy is a result or results close to the actual or true value, and precision is how close a set of measurements are to each other, let's go over here and look at these examples. So we're going to call this example 1. Oops. We're going to call this example 1. Well, my pen's not really wanting to work. Example 2. And example 3. Okay, so in example 1, what you should notice is these hits are really, really close to one another, okay? This is what's known as precision, all right? So right here, we would say, yes, there is precision, okay? There is precision in these results because they are all really close to one another. So when we're talking about measurements, like for mass or density or volume or whatever it is we're measuring in the lab, if those results are really close to each other in value, that is known as precision. Now, are these hits accurate? No, they are not, okay? They have to be accurate, you've got to be close to the actual or true value. And in this dart game, or this bullseye game, whatever it is, whether it's archery or shooting darts, you're supposed to hit the center to be accurate. So no accuracy, but yes, precision. Now, the next one, we would say this is both accurate and the results are also precise, because you can see they're all on the bullseye, okay? So your results are accurate, and then they're all clumped together. That is precision. All right, what about this last bullseye? And so every year I have students that aren't sure about this, and I want you to make sure that you are aware of what this or how you interpret this. So first of all, are they accurate? And in example 3, you couldn't say no. You have to circle yes. The reason why you have to say that there is accuracy, because one time there is one little dot here where there was accuracy experienced. So you can't say no, because they did in fact experience accuracy in these hits, but it was only one time. Now, in terms of scientific data and collecting measurements and doing data analysis, we don't like results like this. Yeah, sure, they were accurate one time, but we don't want that. You want consistent accuracy like there is in example 2 right here, okay? So you want to be accurate and precise. And in this example, they have one instance of accuracy, but do they have precision? Absolutely not. Their hits are all over the place, all right? They are not close to one another. So this would be an example of being accurate but not having precision, okay? And you really don't want this. You want consistent accuracy. So that would be like if I did these density results again, and let's say that you saw for your density and you got 2.71 grams per cubic centimeters for your sample of aluminum. And again, this is what is the accepted textbook true actual value for aluminum, okay? And so, I know that's messy, I'm sorry. All right, but let's say that you solve the density again and you get like 7.05 grams per cubic centimeter. And then you do it again and you get 1.99 grams per cubic centimeter. All right, so this would be like these results here, where you've got one instance of accuracy right here, okay? But then these aren't even anywhere close. So there's one instance of accuracy but no precision. So you could also, just to kind of go off on another example, let's say that you solve for the density of your sample, and let's say that of your sample of aluminum, and let's just say that you did that your results were 3.6 grams per cubic centimeter the first time, okay, in your first trial. In your second trial of solving for the density, you got 3.61 grams per cubic centimeter, and then you got 3.59 grams per cubic centimeter. So this is the density that you got in 3 trials. Okay, so these type of results for when you collect measurements would be like this up here. It would be like number 1, where you've got precision. So all of your results are really close to one another in value, but they are not accurate, because the accepted true value, the known value for aluminum always is 2.7. All right, so this would be precision but no accuracy. It's like, great, you got your stuff all grouped together, but it's not right. Okay, so what we want in terms of when we are basically doing data analysis, what we want is what we have right here, and that is you want to have this. You want accuracy and precision to be present in your results, okay? All right, so the second portion of this in terms of data analysis, so this is all about like analyzing your data and really like describing it in words and in calculations. And so the calculation part, this is where we are going to solve for something known as percent error. All right, so percent error has a formula. All right, the percent error formula involves two values, two measurements. One, there's the actual value. So you know how I said that aluminum earlier has a density that is 2.7 grams per cubic centimeters always? Well, that would be what we call aluminum's actual density. Actual, it's usually called actual. Sometimes it's called the true value. Sometimes it's called the literature value, like the textbook value. Actual, true, what's the other one? I'll say it. Y'all know it because I'll say it. But basically, this is the one it's supposed to be, right? Like, this is what you're supposed to get, all right? Whenever you calculate for the density of any sample of aluminum, whether it's this tiny or whether it's like a huge ball of aluminum, okay? Now, the other measurement that is involved is going to be the measured value. So the measured value is what you, as the student, the teacher, the scientist in the lab, this is what you actually get in the lab. So this can be known, is also called like the experimental value. This is what you get, or the person that's doing the experiment, and this is what you should get, what you should have gotten, okay? And you're going to plug these in to solve for something known as percent error. So do notice that the actual value shows up twice. So this right here is in the numerator of this formula. It's also in the denominator, okay? So really important that you realize it's the actual value that shows up in the top and bottom, not the measured value, okay? It only shows up in the numerator. All right, so let's do a practice problem with this, okay? I've got some that you can practice here at home, but I'm going to give you just an example with this. So let's say that you solve, that you and your lab partner solve for the mass and volume of a piece of aluminum, and then once you've done that, you record or you calculate and you get a density of 3.1 grams per cubic centimeter for your piece of aluminum, okay? So now you're going to take this to solve for what is known as percent error. You are now going to take these two values and plug them in where they go in this formula, okay? So the actual value, that is the value that you should have gotten, is 2.7, okay? So we're going to put 2.7 right here. 2.7 minus the measured value that is 3.1. So this is what you got experimentally, was 3.1. Now I'm not going to put all the units in there because that's not necessary. Now notice that there are absolute value symbols right here. That's because you should never get an absolute value. Means that it eliminates any negative values you may get when you subtract these, okay? So if it ends up being negative, then just get rid of it, all right? So this is 2.7 minus 3.1 over the actual value again, which is 2.7. So we're going to say 2.7 minus 3.1. You're going to get negative 0.4, but I'm just going to write 0.4 because these absolute values symbols will allow me to get rid of that negative. So percent error, I now have 0.4 divided by 2.7. Yeah, you're probably going to get a decimal. You're going to get a number less than 1, which is perfectly fine because we're going to actually multiply this by 100. So you end up getting right here 0.14 okay? You've got several more digits, but I'm just going to keep 3 decimal place values. When you do these 3 decimal place values is pretty standard because we're going to turn this into a percent with 1 decimal point. So notice right here, over here in the formula, that you then, once you have calculated this right here, you're going to then multiply by 100, all right? Which means that the decimal is just going to be moved over twice. So we're going to say 0.148 times 100, which is going to get me a percent error of 14.8, 8%. All right, I know that 8 is really ugly, but 14.8%. So what this means is that when this was calculated, your results, your measured or experimental value that you and your lab partner got is 14.8% wrong. Like it's 14.8% off the correct answer, okay? So when you take a quiz or a test, and let's say on a test you make an 80, your percent error is 20, all right? You've got a 20% error. So right here, your results are over the actual value by 14.8%. And that is what is known as percent error, okay? So we're going to practice with these in class. Just want to give you an idea of what both of these things are. Precision versus accuracy, and percent error are very essential in terms of doing data analysis.